Some galaxies appear older than the universe itself. This is not science fiction, but a genuine cosmic puzzle emerging from our most powerful telescopes. At first glance, it sounds like an impossibility, a flaw in our fundamental story of creation. How could a structure exist before time began? Yet this paradox is not a sign that cosmology is broken, but a signal that we are on the verge of a profound discovery. By the end of this journey, you will understand how this apparent contradiction is reshaping our entire view of the cosmos's first moments. We will untangle how measurement tricks the eye, how the first stars might have ignited with impossible speed, and whether our universe's infancy holds secrets physics has yet to name. What does it truly mean for something to be ancient? This timeline of 13.8 billion years is our cosmic bedrock, the most precisely measured number in all of science. It comes not from guesswork, but from listening to the universe's first light. After the Big Bang, the newborn cosmos was a searing, opaque plasma of particles and energy. Then, after about 380,000 years, it cooled enough for atoms to form, allowing light to travel freely for the first time. That ancient flash, now stretched and cooled by the universe's expansion, still washes over us today as a faint, uniform glow in every direction. We call it the cosmic microwave background. Space telescopes like Planck have mapped its subtle temperature variations with incredible precision, and those tiny wrinkles are a frozen baby picture of the universe. By reading the physics encoded in that image, scientists can calculate backward to the moment of the Big Bang itself. That calculation gives us the number 13.8 billion years. It is the ultimate starting gun for the cosmic race. Every star, every galaxy, every planet we will ever find was born sometime after that moment. So when we point our telescopes at a distant galaxy and say it appears to be older than that, we are not just questioning a date. We are challenging the very foundation of our cosmic chronology, suggesting something might have started running before the clock even began to tick. But here is where our cosmic detective work begins. When we say a galaxy appears older than the universe, we are not claiming it has a single, simple birthday. A galaxy is not born in an instant like a star igniting. Instead, its age is a story told by its oldest citizens. Astronomers define a galaxy's age by studying its most ancient stellar populations. Think of it like walking into a grand, bustling city. You could ask when the city was founded, but a more telling question is, how old are the oldest buildings still standing? Those ancient structures hold the true origin story. In a galaxy, the oldest buildings are its first generation of stars. To find their age, scientists use the universe's own instruction manual for stars, the laws of physics that govern how they live, change, and grow old. By analyzing the light from a distant galaxy, astronomers can sort its stars using a powerful tool called the Hertzsprung-Russell diagram. This chart plots a star's brightness against its color, and every star follows a predictable path on this map as it ages. Spotting where the majority of a galaxy's stars fall on this diagram reveals their stage in life. Furthermore, the chemical fingerprint of that starlight is crucial. The very first stars in the cosmos were made almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They lived fast, died young, and in their spectacular endings, they forged heavier elements like carbon, oxygen, and iron in their cores. We call these heavier elements metals in astronomy. So a star with very low metallicity is a sign of an ancient origin, a member of that first pioneering generation. By combining these clues, the stellar life cycles and the chemical makeup, astronomers build a model and estimate a date for when those first stars must have formed. It is a brilliant piece of cosmic forensics, but it is vital to remember it is an inference, a calculated estimate based on our understanding of physics. It is not a direct timestamp from the dawn of time. This estimation is our best tool, but like any tool, its reading depends on how we calibrate it, and sometimes the readings it gives are, frankly, bewildering. The shockwave hit astronomy in the late 1990s. The Hubble Space Telescope, freed from the blurring effect of Earth's atmosphere, pointed its eye at a seemingly empty patch of sky for days. This was the Hubble Deep Field, a long-exposure stare into the abyss. What it brought back was not emptiness, but a universe teeming with countless faint, smudgy lights, each one a galaxy billions of light-years away. Astronomers eagerly sifted through this treasure trove of infant galaxies, expecting to see the building blocks of the cosmos, small, blue, chaotic clumps of young stars, the toddlers of the universe. And they found them. But they also found something that made no sense, lurking at the very edge of observable space, at staggering distances that meant their light had been traveling for over 90% of the universe's lifetime, were galaxies that looked nothing like infants. They were massive, surprisingly bright, and most tellingly, they glowed with a deep, ruddy color. In the language of starlight, red means old. Blue starlight comes from hot, young, massive stars that burn out quickly. Red light comes from cooler, older, longer-lived stars. These distant smudges, seen as they were just a few 100 million years after the Big Bang, displayed the calm, settled redness of a mature stellar population. They were not chaotic nurseries. They were established neighborhoods, cosmic cities that seemed to have been built with impossible speed. The universe, according to our best timeline, was a toddler itself, yet here were galaxies that appeared to be middle-aged. It was as if archaeologists, digging for the origins of human civilization, unearthed not simple tools and campfires, but the ruins of a gleaming, fully formed metropolis. The finding defied every model of how galaxies grow slowly, accumulating mass over billions of years. This was the discovery that lit the fuse on our puzzle. Astronomers had a new, jarring term for them: mature galaxies in the infant universe. Their very existence asked a blunt, unsettling question. Did these galaxies simply form with astonishing, inexplicable haste, or was our measurement of cosmic time itself somehow flawed? The discovery of those unexpectedly mature galaxies was just the opening act. For decades, astronomers wrestled with the Hubble data, refining models and hoping more powerful instruments might offer clarity. Then, in the summer of 2022, the James Webb Space Telescope opened its golden eye. Its mission was to see farther back and with sharper clarity than ever before. It delivered, and in doing so, it turned a puzzling mystery into a full-blown cosmic crisis. Among its first breathtaking deep-field images was a collection of galaxies so distant their light was emitted when the universe was a mere 300 to 400 million years old. They should have been the faintest, most primitive blue blobs imaginable. Instead, Webb saw something astonishing. These early galaxies were not just present, they were often massive, compact, and glowing with the distinctive red hue of old stars. One of the most striking examples is nicknamed the Sparkler Galaxy. Seen as it was just a few 100 million years after the Big Bang, this galaxy is dotted with what appear to be ancient globular clusters, dense swarms of stars that, in our own Milky Way, are some of the oldest known objects in existence. The Sparkler and its contemporaries are not just early, they are precociously evolved. Their light tells a story of stars that had already lived long lives, burned through their fuel, and enriched their surroundings with heavy elements, all within a cosmic heartbeat. This is where the paradox becomes data-driven and inescapable. Hubble's findings could be questioned as pushing the limits of its technology, but Webb is an instrument of unprecedented power, built specifically to see this era. Its data is clear, precise, and relentless. These galaxies are not just red because of cosmic dust. their spectral signatures confirm the presence of old stellar populations. The timeline simply does not add up. If the universe is 13.8 billion years old, and it takes time for gravity to pull matter together, for gas to cool and collapse into stars, and for those stars to age, then these galaxies appear to have accomplished in a few 100 million years what we thought should take billions. It is as if you gave a child a pile of lumber and returned an hour later to find not a simple treehouse, but a finished, furnished cathedral. The tools and the time provided seem utterly insufficient for the result. Webb's observations did not create the age puzzle, but they sharpened it to a fine, undeniable point, forcing every cosmologist to re-examine the very first chapters of our universal story. The James Webb Telescope's observations hinge on a single, elegant phenomenon, a kind of cosmic time machine built into the very fabric of space. This phenomenon is called redshift. To understand the paradox of ancient-looking galaxies, we must first understand how we know they are so profoundly old in the first place. Redshift is the universe's own historical record, a permanent change etched into the light from distant objects. Imagine the sound of a siren on a passing ambulance. As it moves toward you, the sound waves are compressed, making the pitch higher. As it moves away, the waves are stretched, making the pitch lower. This is the Doppler effect, and light behaves in a remarkably similar way. When a distant galaxy moves away from us, the light it emits gets stretched on its long journey across the cosmos. Since longer wavelengths of light appear more red to our eyes, this stretching is called a redshift. The faster the galaxy recedes, the greater the redshift. But here is the crucial, mind-bending part. It is not just that galaxies are moving through space. Space itself is expanding, carrying galaxies along with it like raisins in a rising loaf of bread. The farther away a galaxy is, the more expanding space there is between us and it, and the faster it appears to be receding. This means redshift becomes a direct measure of cosmic distance. A higher redshift number tells us an object is farther away, and because light takes time to travel, looking far away is the same as looking back in time. When we observe a galaxy with a very high redshift, we are not seeing it as it is today. We are catching a glimpse of it as it was in the universe's deep past, sometimes when the cosmos was only a few % of its current age. So, when astronomers report finding a mature-looking galaxy at a redshift of 10 or 12, they are saying they see a snapshot of that galaxy as it existed just a few 100 million years after the Big Bang. That light has been traveling for over 13 billion years to reach us. This is not an estimate or a guess. It is a fundamental property of the light itself, a readout from the universe's clock. Redshift is the unwavering ruler that places these puzzling galaxies firmly in the nursery of cosmic time, making their apparent maturity not just surprising, but a direct challenge to our models of how quickly a galaxy can grow up. So the redshift measurement is our cosmic clock, placing the galaxy at a specific moment in the past. Now we can see the mathematical heart of the paradox. Let us walk through a simplified yet real calculation. Suppose the James Webb Space Telescope observes a galaxy at a redshift of 10. This powerful number tells us the light we are seeing left that galaxy when the universe was only about 480 million years old. From our perspective here and now, that means we are looking back roughly 13.4 billion years into the past. It is a snapshot from an era so ancient it defies easy comprehension. Next, astronomers analyze the starlight from this distant smudge. They fit the data to models of how stars evolve, and the best fit suggests the dominant stellar population within that galaxy is approximately 1.5 billion years old. This is the estimated age of its stars, and here is where the numbers collide in a way that seems to break causality itself. If the stars are 1.5 billion years old at the moment their light began its journey to us, then they must have ignited, they must have begun shining 1.5 billion years before that snapshot was taken. We simply add the two numbers together, 1.5 billion years of stellar age, plus the 13.4 billion years the light has traveled, gives us a total of 14.9 billion years. This is the implied birth date for those first stars, yet our most fundamental cosmic measurement, derived from the cosmic microwave background, tells us the universe itself is only 13.8 billion years old. According to this straightforward arithmetic, those stars began forming a full 1.1 billion years before the Big Bang is said to have occurred. It is a chronological impossibility, a birthday that precedes the birth of time. Visually, picture a grand, ancient tree. You take a core sample and count its rings, finding it to be 100 years old. But then you check the historical record for the land, and the records prove conclusively that the soil it stands in only formed 80 years ago. The tree cannot be older than the ground that holds it. This is the essence of the look-back time conundrum. The galaxy, like that tree, appears to have taken root in soil that did not yet exist. This stark contradiction is not a mistake in the arithmetic. It is the glaring signal that our understanding of the soil, of the universe's earliest conditions, must be missing something profound. This stark contradiction forces us to become cosmic skeptics. Before we rewrite the laws of physics, we must first check our instruments. The first and most significant source of potential error lies in the very measurement that places these galaxies in the deep past. We have spoken of redshift as a cosmic clock, but we must ask, how confident are we in reading that clock? The answer reveals a crucial divide in astronomical technique. The gold standard is called spectroscopic redshift. This involves capturing the galaxy's light and spreading it out into a full rainbow spectrum, a detailed barcode of its chemical composition. Within that barcode are specific, dark lines where elements like hydrogen or oxygen have absorbed light. Because the expansion of space stretches all light uniformly, these absorption lines are shifted from their known positions by a precise, measurable amount. It is a direct, unambiguous reading. However, obtaining a spectroscopic redshift for an extremely faint, distant galaxy requires an immense amount of telescope time on the world's largest instruments. For the thousands of galaxies seen in deep field images, it is simply not practical. So astronomers often rely on a faster but far less precise method, photometric redshift. Instead of a detailed barcode, this technique uses broad color photography. Imagine trying to identify a specific shade of paint not by its name, but by looking at it through just a handful of colored filters. A red filter, a green filter, a blue filter. You make an educated guess based on the overall tint you see. Photometric redshift works similarly. Astronomers image a galaxy through several filters that each capture a specific slice of light from ultraviolet to infrared. They then compare the brightness of the galaxy in each filter to models predicting how a galaxy at different redshifts should appear. If a galaxy looks very red in all the filters, the model might suggest it is at a very high redshift, its light stretched far into the red part of the spectrum. But here is where the trouble can begin. Many things in the universe can make a galaxy look red, not just cosmic expansion. Vast clouds of interstellar dust within a galaxy can act like a cosmic fog, scattering and absorbing blue light, leaving only the redder light to pass through. A galaxy that is actually closer to us but just incredibly dusty can perfectly mimic the ruddy color of a truly ancient, distant one. Furthermore, some galaxies have unusual stellar populations or are of a rare type that our standard models do not account for perfectly. Their intrinsic color might be redder than expected, tricking the photometric method. There is also the risk of contamination. What appears as a single, faint red smudge could, in reality, be two or more galaxies along the same line of sight, a closer, brighter object partially obscuring or blending with a more distant one. The combined light could create a color signature that the model misinterprets as a single, extremely distant source. If any of these errors occur, the consequence is dramatic. A galaxy that is actually, say, 2 billion years old, but is mistakenly placed at a redshift suggesting it is seen just 400 million years after the Big Bang, will create an impossible age paradox. Its measured stellar age will wildly exceed the time available since its erroneously assigned cosmic birthday. This is not a failure of cosmology, but a challenge of observation. It reminds us that the first step in solving any great mystery is to ensure we are not being fooled by a trick of the light. Even if our distance measurements are flawless, the next layer of the puzzle lies in interpreting the starlight itself. Translating the faint, reddened glow from a galaxy 13 billion light-years away into a precise stellar age is not a simple matter of reading a cosmic birth certificate. It is an exercise in sophisticated but inherently uncertain modeling. Think of it like a master chef trying to reverse engineer a complex, centuries-old recipe from just a single spoonful of the finished stew. You can analyze the flavor, the texture, the spices, but multiple combinations of ingredients and cooking times could have produced that exact result. In astronomy, this ambiguity is called a degeneracy. One of the most significant degeneracies directly fuels the age paradox. The light from a galaxy composed of very old first-generation stars, stars born from pristine hydrogen and helium with almost no heavier elements, can look remarkably similar to the light from a galaxy full of younger stars that are, however, rich in those heavier elements, what astronomers call metals. An old, metal-poor population glows with a certain red hue because its stars are genuinely ancient and cool. A younger, metal-rich population can also glow with a similar red hue because the abundance of metals in the stellar atmospheres actually blocks and scatters more of the blue light, leaving a redder color behind. So when we see that telltale red smudge in a distant galaxy, are we looking at a genuinely ancient stellar city, or are we looking at a younger metropolis cloaked in a veil of its own metallic smog? The light alone cannot always tell us for sure. This fundamental uncertainty means that a model assuming low metallicity will spit out an older age estimate, while a model assuming higher metallicity will yield a younger one for the very same observed light. Our interpretation is only as good as our assumptions, and in the uncharted territory of the universe's first few 100 million years, we are still learning what assumptions are safe to make. Beyond metallicity, other modeling choices heavily influence the final age number. One is the initial mass function, which is simply our assumption about how many big stars versus small stars the galaxy formed in its first burst. Big, brilliant stars live fast and die young, flooding a galaxy with blue light, while smaller, redder stars burn steadily for eons. If our model incorrectly assumes the early universe made more small, long-lived stars than it actually did, we will naturally infer an older population. Another critical factor is the star formation history. Did all the stars in this galaxy form in one intense, brief fireworks display, or did they trickle into existence over a longer period? A single, ancient burst of star formation followed by quiet aging produces a very specific light signature. But if star formation was more extended or happened in multiple episodes, the blended light of many different aged stars can mimic the signature of a single, older population. Finally, we must return to the cosmic fog, dust. Interstellar dust grains, smaller than a wavelength of light, are incredibly efficient at absorbing blue light and re-emitting it as heat or scattering it away. A galaxy that is actually quite young but is shrouded in immense, opaque clouds of dust from its own frantic star-forming activity will have its blue light ruthlessly filtered out. What reaches our telescopes is a reddened remnant, a signal that can be almost indistinguishable from the gentle glow of a truly ancient, dust-free stellar retirement community. Each of these factors, metallicity, initial mass function, star formation history, and dust, is a dial on our cosmic model. Turn them one way, and the estimated age of a distant galaxy plummets, comfortably fitting within the young universe. Turn them another based on different theoretical expectations, and the age estimate balloons, creating an impossible paradox. The challenge is that, with current data, multiple combinations of these dial settings can produce a model that fits the observed light perfectly. So, when we hear a headline claiming the discovery of a galaxy older than the universe, it is vital to understand this is not a direct measurement, but the output of a specific set of model assumptions. It is one possible interpretation of the cosmic stew, but perhaps not the only recipe that could explain that single, distant spoonful of light. This cosmic veil of dust is far more than just interstellar grime. It is an active, dynamic player in the story of a galaxy's light, and it holds one of the most persuasive keys to unlocking our age paradox. To understand its power, picture a brilliant summer sunset. The sun is intrinsically white, but as its light passes through the thickest part of Earth's atmosphere at a low angle, the shorter blue wavelengths are scattered away by countless tiny particles. What reaches our eyes are the longer, redder wavelengths, bathing the landscape in a warm, golden glow. Interstellar dust performs this same trick on a galactic scale, but with far greater consequence. Within a galaxy undergoing a ferocious burst of star formation, newborn massive stars flood their surroundings with intense blue and ultraviolet light. But these same stellar nurseries are also filled with vast, opaque clouds of silicate and carbon-rich dust grains, debris from previous generations of stars. This dust does not just dim the light, it selectively filters it. The energetic blue light is absorbed or scattered, while the redder light passes through more easily. The result is a galaxy whose intrinsic, youthful blue brilliance is transformed into a deceptive, ruddy hue. From our distant vantage point, that reddening is precisely the signature we associate with an old, quiescent stellar population that has burned through its hot, blue stars. A galaxy that is actually a chaotic, dusty nursery of infant suns can therefore masquerade as a serene retirement home for ancient stars. This is the degeneracy in its most potent form. An early universe galaxy, seen just a few 100 million years after the Big Bang, could be experiencing its first epic starburst, shrouded in its own primordial soot. To our models interpreting its reddish color, it whispers a lie of great age, creating an illusory timeline that seems to stretch back before time itself. This is where the James Webb Space Telescope moves from being a mere observer to a cosmic detective equipped with the perfect tool. For decades, astronomers studying the early universe were hamstrung by a fundamental limitation. As the universe expands, the light from the most distant objects is not just redshifted from visible blue to visible red. It is stretched all the way into the infrared part of the spectrum, invisible to human eyes and to telescopes like Hubble. Crucially, interstellar dust is also transparent to certain infrared wavelengths. Webb, with its massive gold-coated mirrors and suite of infrared instruments, was built to see this hidden light. It is the equivalent of giving our sunset observer a special pair of goggles that can see through the haze, revealing the true white color of the sun hidden behind the atmospheric filter. For those puzzling red galaxies, Webb's infrared eyes can peer directly through their dusty veils. It can detect the warm thermal glow of the dust itself, heated by the very stars it obscures. More importantly, it can capture the specific spectral signatures of key elements and molecules that are unambiguous indicators of youth. For instance, it can look for the bright emission lines of ionized hydrogen, a telltale sign of furious ongoing star formation, even if that light is buried under dust. By combining this infrared data with the visible light observations, astronomers can begin to disentangle the two effects: how much of the redness is from cosmic expansion and how much is from local dust. Early results from Webb are already doing exactly this. For some of the most extreme candidates, the data suggests their red color is indeed heavily influenced by dust, implying they are younger than initial photometric estimates proposed. The paradox begins to soften. The galaxy is not necessarily a serene elder, but a brilliant, dusty adolescent in a cosmic growth spurt. Its true age now coming into clearer focus thanks to our new ability to see the heat behind the haze. Yet, even if we correct for dust and refine our models, a stubborn possibility remains. What if the early universe was simply a more prolific, more efficient star forge than anything we see today? This leads us to a truly exotic frontier of cosmic theory, one that reimagines the very nature of the first stars. In our local, modern universe, star formation is a slow, inefficient process. Vast clouds of gas must collapse under gravity, but they are supported by turbulence, magnetic fields, and pressure. Only a tiny fraction of a cloud's mass, perhaps 1 or 2%, ever condenses into stars. The rest is blown away by the fierce winds and radiation from those same newborn stars. It is a messy, self-limiting business, but the infant cosmos was a fundamentally different place. For a fleeting window of time, it contained only the pristine elements forged in the Big Bang: hydrogen, helium, and a trace of lithium. There were no heavier elements, no dust grains. This purity had profound consequences. Without dust, gas clouds could not cool as efficiently. Without metals to act as catalysts and radiators, the only way for a cloud to shed energy and collapse was through the faint glow of molecular hydrogen. This peculiar physics may have given birth to the universe's mythical first generation, population 3 stars. Theorists propose these pioneers were not like the stars we know. They could have been colossal behemoths, hundreds of times the mass of our Sun. Such monsters would live spectacularly brief lives, burning through their nuclear fuel in just a few million years before exploding as unimaginably powerful supernova. Their deaths would not just seed the cosmos with the first heavy elements, they would violently disrupt their surroundings, triggering waves of compression that could ignite the next generation of stars almost instantaneously. In this environment, star formation may not have been slow and inefficient. It could have been a runaway chain reaction, a monolithic collapse where an entire giant cloud fragmented into stars in one synchronized, hyper-efficient burst. Imagine the difference between a modern, regulated factory producing one car at a time and the sudden, total conversion of an entire warehouse's worth of parts into a fleet of vehicles in a single explosive event. If the first galaxies formed their stars in such a monolithic, top-down collapse, they could have achieved a mature-looking stellar population in a single, breathtakingly short epoch. A galaxy's entire lifetime of stellar evolution, from the ignition of its first giants to the settled glow of its long-lived smaller stars, could be compressed from billions of years down to a few hundred million. This would dramatically shrink the apparent head start time needed in our calculations. The galaxy is not older than the universe. It simply grew up at a pace we find almost incomprehensible, reaching a state of maturity while the cosmos itself was still in its cosmic infancy. But there is another cosmic magnifying glass, one that literally bends the fabric of space itself. When we peer at the most distant, faintest galaxies, we often rely on a phenomenon called gravitational lensing to bring them into view. This occurs when a massive object, like a foreground galaxy cluster, sits directly between us and a far more distant source. The immense gravity of the cluster warps the space around it, acting like a lens in a giant cosmic telescope. This lens does two remarkable things. First, it magnifies the light from the background galaxy, making it appear brighter and larger than it truly is. Second, it can distort the galaxy's image, stretching it into dramatic arcs or even creating multiple copies of the same object scattered around the lens. This natural telescope has been indispensable for studying the early universe, allowing us to see galaxies that would otherwise be far too faint to detect. Yet we must ask, could this powerful lens also distort our perception of a galaxy's age? The answer is nuanced. the lensing process itself does not change the intrinsic properties of the starlight. The light from a young blue star does not magically become the light from an old red star simply because it passed through a warped region of space. The redshift remains the same and the spectral signatures of the elements are preserved, so in a direct sense, lensing does not create a false age. However, it can introduce a subtle statistical bias known as a selection effect. Gravitational lensing favors certain kinds of objects. The magnification is not uniform. It is strongest for galaxies that lie perfectly aligned behind the very densest parts of the lensing cluster. This means the galaxies we find through lensing are not a random sample of the early universe. They are the ones nature has conveniently brightened for us. This selection could inadvertently skew our observations. For instance, a lens might magnify a galaxy that is already unusually bright and massive for its time, or one that is particularly compact. These could be outliers not representative of typical galaxies in that era. If we then study these magnified outliers and assume they are standard, our models for how quickly galaxies evolve could be thrown off. We might conclude that mature galaxies were common in the infant cosmos, when in fact we are just seeing the rare, overachieving examples that the cosmic lens has chosen to spotlight. It is like trying to understand the average height of a population by only measuring players on a professional basketball team that you observed through a magnifying glass. Your sample is both magnified and pre-selected for extreme stature, leading to a distorted conclusion. So, while gravitational lensing is a priceless tool, it reminds us that in cosmology, seeing something more clearly does not always mean we are seeing it more typically. The cosmic lens reminds us that perspective is everything, yet even with a perfect view, the speed of early galaxy growth demands a hidden engine, a force that could lay the groundwork for stars before the first atom had fully cooled. This brings us to the universe's most elusive architect, dark matter. You cannot see it, touch it, or collect it in a jar. It does not emit, absorb, or reflect light of any kind. Its presence is felt only through its immense gravitational pull, a ghostly hand shaping the cosmos from the shadows. Without it, our universe would look nothing like it does. Galaxies would fly apart, their stars scattering into the void because the visible matter we see, all the stars, gas, and planets, simply does not provide enough gravity to hold these vast structures together. Something invisible, something that outweighs the visible universe by a factor of about 5-to-1, must be providing the missing gravitational glue. This mysterious substance is the unseen foundation upon which every galaxy is built. Its role is not passive, it is the master planner, the first mover in the story of cosmic structure. Long before the first star flickered, dark matter was already at work. In the hot, dense soup of the early universe, dark matter had a critical advantage. Unlike normal matter, which felt the intense pressure of radiation pushing against it, dark matter is unaffected by light. It could begin clumping together under its own gravity almost immediately after the Big Bang, unimpeded by the cosmic fireworks around it. These initial clumps grew over time, merging and attracting more dark matter, eventually forming vast spherical clouds known as dark matter halos. Picture a halo not as a glowing ring, but as an invisible, mountainous landscape of gravity, a deep, spherical well in the fabric of space. These halos became the cosmic construction sites. Ordinary matter, the hydrogen and helium gas, later flowed into these gravitational wells. As the gas settled, it cooled, condensed, and finally ignited into the first stars, giving birth to the galaxies we see. So every brilliant spiral and elliptical galaxy we observe is merely the visible jewel set within a much larger, invisible crown of dark matter. The halo came first. Its size, its shape, and crucially, the timing of its formation dictated everything that followed. This is where the age paradox finds a potential and deeply fascinating resolution. Our standard models make specific predictions about how quickly those first dark matter halos could have grown massive enough to attract the vast reservoirs of gas needed to forge a giant galaxy. But what if our understanding of dark matter itself is incomplete? What if certain properties of this enigmatic substance allowed these gravitational scaffolds to form much earlier than we thought possible? If the first giant dark matter halos collapsed just a few 100 million years after the Big Bang, instead of the billion or more years our standard timeline suggests, then the clock for galaxy assembly starts ticking far sooner. The gas would have had a head start, flowing into these ready-made gravitational wells at the earliest possible moment. Star formation could then begin in earnest, not as a slow trickle, but as a sudden, prolific burst. In this scenario, a galaxy observed at 400 million years after the Big Bang might not need its stars to be impossibly ancient. Instead, its dark matter foundation could have been laid down astonishingly early, providing the time needed for its stellar population to evolve to that point of red maturity we observe. The galaxy is not older than the universe. Its invisible skeleton simply formed with unexpected haste, allowing its visible body to grow up on a radically accelerated schedule. This idea shifts the mystery from the stars we see to the invisible architecture we cannot, suggesting that the solution to one of cosmology's greatest puzzles may be written in the hidden script of dark matter itself. For nearly 3 decades, one elegant framework has held the universe together, at least on paper. It is called the Lambda-Cold dark matter model, often just Lambda-CDM. This is the standard model of cosmology, the official playbook for how our universe evolved from a hot, dense singularity into the vast cosmic web we see today. Its name reveals its 2 central, mysterious ingredients. Lambda represents dark energy, the enigmatic force accelerating the universe's expansion. Cold dark matter is that invisible, slow-moving gravitational glue that forms the cosmic scaffolding. Together, within this model, the entire history of the cosmos unfolds with mathematical precision. It predicts the large-scale structure of galaxy clusters, the subtle patterns in the cosmic microwave background, and the abundance of light elements from the Big Bang. Its predictive power has been nothing short of spectacular, earning it the title of the concordance cosmology. But even the most successful theories face moments of profound testing. The discovery of mature galaxies in the infant universe is exactly that, a direct and serious challenge. It creates a growing tension between the model's beautiful predictions for the universe as a whole and the messy, complicated reality of how the very first structures actually formed. This is not a call to tear down Lambda-CDM. Its large-scale successes are far too robust to discard. Instead, the early galaxy crisis points to a critical gap in our understanding. Think of it like a master architect's blueprint for a magnificent city. The blueprint perfectly specifies the placement of major highways, power grids, and water systems. It is flawless on the grand scale, but when the first construction crews arrive, they find that the instructions for laying the very first foundations, for mixing the initial concrete and setting the cornerstones of the very first buildings, are incomplete or perhaps even slightly off. The city still gets built, but those first structures emerge in surprising, unexpected ways. The Lambda-CDM model is that brilliant large-scale blueprint. It tells us with incredible accuracy how the dark matter halos should have formed and grown over billions of years. Where it struggles is in the fine print, the so-called small-scale physics. This is the immensely complex dance of normal matter, the gas cooling, collapsing, fragmenting, and igniting into stars within those dark matter halos. The processes of star formation, stellar feedback, and the role of magnetic fields in the primordial universe are fiendishly difficult to model. The early, massive galaxies suggest that in the universe's first chapters, this dance may have been far more rapid and efficient than our current small-scale recipes allow. The blueprint is sound, but we are still learning how to read the instructions for the very first bricks. The Standard Model's blueprint faces its toughest test not in the heavens, but inside the world's most powerful supercomputers. To see if our cosmic story holds together, scientists build entire universes from scratch within lines of code. These are cosmological simulations, vast digital experiments that take the known laws of physics and the Lambda-CDM framework, set the initial conditions to match the cosmic microwave background, and then press play. The simulation runs the clock forward from the Big Bang, watching as dark matter clumps into halos, gas flows in, cools, and eventually forms stars and galaxies. It is a breathtaking endeavor, a virtual time machine, and for the most part, these simulated universes look remarkably like our own, reproducing the cosmic web of filaments and voids with stunning accuracy. But when researchers zoom in on the era of the first galaxies, a persistent and telling problem emerges. The simulations have a very hard time creating galaxies as massive and as evolved as the ones James Webb is showing us. When they do manage to form big galaxies early, it often happens for the wrong reason, exposing a flaw in our physics called the overcooling problem. Here is how it unfolds in the digital cosmos. Gas falls into a young dark matter halo, drawn in by gravity. As the gas compresses, it heats up. To collapse further and form stars, it must shed this heat, it must cool. In the early, metal-free universe, cooling was inefficient, which should have slowed everything down. But in many simulations, the gas cools too quickly and too completely. It rushes to the center of the halo unimpeded, converting almost wholesale into a burst of stars. This creates a galaxy that is too massive, too bright, and too red too soon. It solves the observation by breaking a different piece of physics, because we know star formation cannot be that efficient. If it were, the early universe would have burned through its fuel in a frenzy, leaving nothing for the billions of years of galaxy growth that followed. The overcooling problem reveals a critical missing ingredient in our recipes, a regulatory force that must have been present to slow things down, to make star formation messy and inefficient, even in those pristine conditions. That missing ingredient is feedback. In a modern galaxy, star formation is a self-regulating cycle. When massive stars are born, they do not shine quietly. They flood their surroundings with intense radiation and powerful stellar winds. And when those short-lived stars die, they explode as supernova, releasing blasts of energy that can heat surrounding gas, push it away, and even enrich it with heavy elements. This violent activity disrupts the very cloud that gave the stars birth, shutting off further star formation for a time. It is a cosmic balancing act, a burst of creation followed by a period of enforced quiet. The same is true for supermassive black holes at the centers of galaxies. When they actively feed on matter, they can become quasars, emitting jets and radiation so powerful they can blow gas out of the galaxy entirely, quenching star formation on a galactic scale. This stellar and black hole feedback is the universe's built-in thermostat, preventing the unchecked cooling and collapse that leads to overcooking, or rather, overcooling. The mismatch between simulations and Webb's observations suggests that in the universe's first few 100 million years, this thermostat may have been set differently than we assumed. Perhaps the first supernova from those hypothetical population 3 giants were far more energetic than their modern counterparts, providing a more potent, earlier form of feedback that actually helped trigger the next wave of star formation in a coordinated way, rather than just shutting it down. Or perhaps the first black holes grew with astonishing speed, turning on their regulating quasars earlier than our models allow. The data is telling us that whatever the precise mechanism, the processes that govern the birth and death of stars and the interplay between stars and black holes must have been exceptionally effective and rapid in the primordial cosmos. The galaxies we see are not the product of runaway cooling. They are the signature of a powerful, dynamic, and finely tuned cycle of creation and destruction operating at a pace we are only beginning to comprehend. The simulations are not wrong, they are incomplete. Each puzzling red galaxy is a clue, helping us add the missing lines of code for the universe's earliest and most dramatic acts of self-regulation. A definitive answer requires a cosmic barcode. Photometric redshifts, those educated guesses based on color, have brought us to the edge of discovery, but they cannot take us across the threshold. They are like identifying a distant forest by its overall greenish hue. You know it is vegetation, but you cannot tell if it is a young pine grove or an ancient redwood forest without examining the leaves up close. For a galaxy, that close examination is a spectrum. Obtaining a spectrum means capturing the galaxy's light and spreading it out into its constituent rainbow, revealing a detailed pattern of bright emission lines and dark absorption lines. These lines are the unique fingerprints of specific elements: hydrogen, oxygen, magnesium, imprinted on the light by the galaxy's stars and gas. The expansion of the universe does not just dim or redden this light. It stretches the entire rainbow, shifting every single fingerprint by the same exact amount. A spectroscopic redshift measures this shift with exquisite precision, giving us an unambiguous, unassailable distance. There is no confusion with dust reddening here. The pattern itself is the proof. Furthermore, the relative strength of these lines tells a rich story about the galaxy's true nature. They reveal the temperature of its stars, the density of its gas, and crucially, its chemical composition. Is it metal poor, a sign of primordial youth, or metal rich, suggesting a more mature, evolved population? The spectrum holds the answer. This is the gold standard, the courtroom evidence that moves a candidate from an intriguing possibility to a confirmed fact. For decades, this evidence was nearly impossible to get for the universe's first galaxies. They were simply too faint, their light stretched too far into the infrared. Capturing enough of their photons to spread into a readable spectrum required hundreds of hours on the world's largest ground-based telescopes, and even then, success was rare. The James Webb Space Telescope has shattered this barrier. Its colossal light-gathering mirror and exquisitely sensitive infrared spectrographs are built for this exact task. Where Hubble might see only a faint red smudge, Webb can dissect that smudge's light into a detailed spectral barcode. In a matter of hours, not weeks, it can obtain a spectrum that definitively pins down a galaxy's redshift and begins to decode its stellar life story. Already, Webb is doing this for the most extreme candidates, transforming them from photometric mysteries into spectroscopic subjects. Each confirmed spectrum is a cornerstone, a solid data point upon which we can begin to rebuild our timeline of cosmic dawn with newfound confidence. The age paradox will not be solved by speculation, but by this slow, meticulous accumulation of light, stretched into rainbows and read like the universe's own ancient text. History offers a powerful lesson in cosmic humility. The very first deep-field images from the Hubble Space Telescope in the 1990s sparked a similar, though less severe, age controversy. Astronomers identified several faint, red galaxies at what were then considered extreme distances. Their photometric redshifts suggested they were seen when the universe was less than 1 billion years old, yet their red colors implied stellar populations already several billion years in age. The headlines wrote themselves: had Hubble discovered galaxies older than time? The scientific community, however, did not stop at the headline. It engaged in a slow, meticulous process of follow-up. Larger ground-based telescopes spent precious observing time to capture the spectra of these puzzling objects. One by one, the spectroscopic data told a different story. For many of these candidates, the true redshift was significantly lower than the photometric estimate. They were not ancient giants from the cosmic dawn, but closer, dustier galaxies whose light had been misinterpreted. The impossible age paradox evaporated, not because the laws of physics changed, but because our data improved. This is not a story of failure, but of the scientific method working exactly as it should. A startling observation creates a hypothesis: perhaps these galaxies are impossibly old. That hypothesis makes testable predictions. Their spectra should confirm the high redshift. New, more precise observations then test those predictions. When the data contradicts the initial idea, the hypothesis is revised. The universe did not change. Our understanding of it simply became clearer, refined by better tools and more rigorous measurement. This historical precedent is a vital reminder as we confront Webb's extraordinary findings today. We are in the hypothesis stage, surrounded by breathtaking but preliminary data. The current age estimates, while compelling, are built on the same foundation of photometric redshifts and stellar population models that were proven uncertain before. The next crucial phase has already begun. Webb itself, along with the next generation of giant ground-based telescopes, is now gathering the spectroscopic evidence that will separate cosmic reality from tantalizing illusion. The process is repeating on a grander scale and with higher stakes. Each definitive spectrum acts as a keystone, locking a distant galaxy into its true place in cosmic history. Some of today's most extreme candidates may, like their Hubble-era predecessors, be revealed as closer or dustier than they appear. Others may hold their ground, confirming that the early universe truly was a place of astonishing and rapid assembly. The path forward is not blind speculation, but patient, persistent observation. The story of the cosmos is written in light, and we are only now learning to read its most ancient sentences without error. Spectroscopic data will anchor our timeline, but what if the anchor itself is drifting? The most profound resolution to the age paradox would not involve tweaking our models of star formation, but rewriting the fundamental physics that governs the cosmos. This path leads beyond the comfortable realm of the lambda cold dark matter model into speculative, radical territory. If galaxies truly formed with impossible speed, perhaps the rules of the game were different in the early universe. One audacious idea challenges the very force that sculpts cosmic structure, gravity itself. For decades, a minority of physicists have proposed that Einstein's theory of general relativity, while spectacularly successful on large scales, might require modification in the weak gravity regimes of galaxy outskirts. This framework is known as modified Newtonian dynamics, or MND. Its core proposition is simple yet staggering. What we attribute to the gravitational pull of invisible dark matter is actually a slight alteration in how gravity itself behaves at extremely low accelerations. If such a modification were real, it could dramatically change the predicted timeline for structure formation. Without the need for dark matter halos to slowly coalesce over billions of years, the gravitational scaffolding for galaxies could snap into place almost instantaneously after the Big Bang. Gas would collapse into stars under this enhanced gravity at a breakneck pace, potentially allowing mature galaxies to emerge in a fraction of the time our standard models allow. While MND has had notable successes explaining certain galactic rotation curves without dark matter, it struggles mightily to account for the large-scale evidence from the cosmic microwave background and galaxy clusters that firmly supports the Lambda-CDM picture. Yet its persistence highlights a deep truth. When observations persistently defy expectation, even our most cherished laws become subjects for re-examination. Another radical possibility is that the universe's constants are not so constant after all. The speed of light, the strength of gravity, the fine structure constant that dictates how atoms interact with light, these are the immutable numbers we plug into every cosmological equation. But what if one or more of these constants were slightly different in the primordial universe? A subtly stronger force of gravity in the first few 100 million years would have turbocharged the collapse of gas clouds, making star formation explosively fast. A slightly different fine structure constant could have altered how efficiently the first stars burned their fuel, changing their lifetimes and the light they emitted, which would directly affect our age estimates when we look back at them. These are not ideas proposed lightly. They would overturn a cornerstone of modern physics. Yet researchers have looked for such variations for years, studying the light from incredibly distant quasars for any sign that the ancient laws of nature differed from our own. So far, the evidence suggests the constants have remained steady, but the search continues, driven by the kind of deep mysteries that early galaxies present. Finally, the properties of dark matter itself might hold the key. Our standard model assumes it is cold, meaning its particles move slowly, and that it only interacts through gravity and perhaps the weak nuclear force. But what if dark matter is not perfectly cold? What if it has some internal complexity, some way to interact with itself or with radiation? So-called warm or self-interacting dark matter would behave differently in the early universe. It would resist clumping on very small scales, potentially delaying the formation of the very first small halos. This might sound like it would make the problem worse, but the consequence could be a cosmic bottleneck. Once conditions were right, structure formation might then proceed in a sudden, coordinated avalanche, leading to the rapid, synchronized birth of massive galaxies rather than a slow, steady trickle. It is a cosmic traffic jam followed by a green light for everyone at once. These ideas, modified gravity, varying constants, exotic dark matter, are the frontier of cosmology. They are not yet mainstream, and they each face significant hurdles in explaining the full suite of cosmic data. But their very existence is a testament to the depth of the mystery we are confronting. When the most careful observations persistently clash with our best theories, it is not a sign of failure. It is the universe whispering that there is more to the story, perhaps written in a physics we have not yet learned to read. The galaxy's frantic adolescence may have been fueled by a hidden, ravenous heart. Among the most startling discoveries from the infant cosmos are not just mature-looking galaxies, but the supermassive black holes found at their centers. These are not the quiet, dormant giants of later times, but active, feeding monsters, visible as brilliant quasars, shining with the light of 1 trillion stars. And here is the truly baffling part. Some of these quasars are seen when the universe was less than 700 million years old. Yet their black holes already weigh in at over 1 billion times the mass of our Sun. To grow that large, that fast, defies our standard models of black hole growth. It would be like finding a toddler who already weighed as much as a blue whale. The conundrum is parallel to the galaxy age puzzle, and the two are almost certainly intertwined. These are not separate mysteries, but two sides of the same cosmic coin. The galaxy and its central black hole appear to have grown up together at a breakneck pace that suggests their fates were linked from the very beginning. In our local universe, we see a correlation between a galaxy's central bulge and the mass of its supermassive black hole, implying a long, slow dance of co-evolution over billions of years. But in the primordial universe, this dance may have been a feverish, accelerated sprint. The black hole could have formed from the direct collapse of an immense gas cloud, bypassing the stage of a small stellar remnant and starting life as a heavyweight seed containing tens of thousands of solar masses. This gargantuan seed would have had a voracious appetite from birth, pulling in the surrounding pristine gas at a phenomenal rate. As it fed, it would have blazed as a quasar, pouring torrents of energy into the galaxy. This energy is not just light, it is a powerful regulatory force. The intense radiation and supersonic jets from the quasar would have heated the surrounding gas, driving massive outflows that both fueled further star formation in some regions and shut it down in others. This violent feedback could have orchestrated the galaxy's growth, creating a rapid, punctuated cycle of starbirth and quenching that compressed billions of years of evolution into a few 100 million. In this scenario, the galaxy does not slowly build a bulge and then grow a matching black hole. Instead, the black hole and the galaxy are born together in a frenzy of mutual creation and destruction, racing each other to maturity under the unique, dense conditions of the cosmic dawn. The red, mature-looking starlight we see may be the signature of that first, intense wave of star formation, suddenly quenched by the awakening of the monster at the galaxy's heart, leaving behind a population of aging stars while the black hole continued to feast. This different pathway to maturity, a symbiotic explosion of stellar and black hole growth, could resolve both puzzles at once, painting a picture of a first cosmic generation that lived fast, died young, and left behind a legacy of impossible-seeming giants. The furious growth of those first galaxies and black holes did more than just defy our timelines. It permanently transformed the very medium of the cosmos. To understand the true impact of these precocious structures, we must step back into the universe's first great transition, a period known as the Epoch of Reionization. For hundreds of millions of years after the Big Bang, space was not the crystal-clear void we imagine. It was filled with a dense, neutral fog of hydrogen gas. This primordial haze absorbed the energetic ultraviolet light, keeping the cosmos in a kind of dark age, punctuated only by the faint glow of the cooling cosmic background radiation. Then something changed. The first sources of intense light switched on. These were the brilliant, massive population 3 stars and the searing quasars at the hearts of the earliest galaxies. Their radiation was so powerful, so packed with ultraviolet photons, that it began to tear electrons away from the hydrogen atoms surrounding them. This process, called ionization, started to carve transparent bubbles in the opaque cosmic fog. Imagine a dense morning mist blanketing a landscape. As the sun rises, its light burns holes in the mist, creating clear patches that slowly expand and merge until the entire valley is bathed in daylight. Reionization was that sunrise on a cosmic scale, but it was a chaotic, patchy process that took hundreds of millions of years. The very galaxies that seem impossibly old to us were likely the brilliant beacons driving this universal transformation. Their intense, frantic radiation was the tool that cleared the fog, ending the cosmic dark ages and making the universe transparent to light as we see it today. This context is crucial for our puzzle. A galaxy in the midst of reionization is not a serene object. It is a cosmic lighthouse blazing in a storm of its own making. The environment around it is violently ionized, flooded with harsh ultraviolet radiation. This extreme environment has a direct effect on the light we receive. The intense radiation can heat the gas, suppress certain wavelengths of light, and even alter the apparent colors and spectral signatures we use to date the stars. A galaxy's light, after fighting its way through this turbulent, ionized medium, may arrive at our telescopes carrying the scars of that journey, potentially skewing our interpretation of its stellar population. What looks like the calm, red glow of an ancient retirement community might instead be the filtered, reddened glare of a brilliant youth shining through a cosmic battlefield. This cosmic dawn was not a quiet sunrise but a revolution. Yet as we piece together its story from ancient light, we must confront a subtle, philosophical filter shaping everything we see. Our entire science of cosmology operates under a profound, often unspoken limitation. We are not impartial observers floating outside the universe. We are products of it, living inside the very system we are trying to measure. This leads to a fundamental selection bias sometimes called the Anthropic Shadow. We can only ask questions about a universe that has already produced creatures capable of asking them. We exist in a cosmic neighborhood that, over billions of years, developed the right conditions for planets, chemistry, and ultimately, life. This is our observational platform, our one and only window. The consequence is that our entire view of cosmic history is filtered through the lens of what led to us. We naturally assume the processes we see in our local, mature universe, the slow growth of galaxies, the steady pace of star formation, are the universal norm. They are the rules that allowed our own story to unfold. But what if our galactic neighborhood is not the rule, but the exception? What if the frantic, explosive assembly seen in the early universe was actually the standard mode of operation for most of cosmic history, and we simply live in the quiet, slow-motion aftermath? The galaxies that seem impossibly old and massive might not be outliers. They could be the typical pioneers, the standard products of a young, dense, and wildly energetic cosmos. Our local experience, by contrast, could be the atypical one, a peaceful backwater where the furious physics of creation has long since settled into a gentle simmer. This perspective flips the puzzle on its head. The question is not why those early galaxies are so strange, but why our later ones are so sedate. The answer likely lies in that very evolution. As the universe expanded and thinned out, as dark energy began to dominate, the conditions for such rapid, monolithic collapse simply vanished. The age paradox, then, becomes a signpost marking a transition from one cosmic era to another. It highlights a universe that changed its fundamental behavior over time, with us arriving far too late to witness the main event, only seeing its fading afterglow. This does not mean our models are wrong, but it powerfully suggests they are incomplete, still colored by the quiet corner of spacetime we happen to call home. The light from the dawn is challenging us to remember that we are not just observers of the universe, but also its unlikely and perhaps sheltered children. There is another, more dynamic way to build a cosmic metropolis almost overnight. Picture two thriving, vibrant cities on a collision course. Each is a hub of frantic construction, filled with young, brilliant skyscrapers glowing with blue-white light. They are not ancient relics but bustling centers of industry. Now imagine these two cities merging into one colossal urban center in a cataclysmic event. The collision would be unimaginably violent, triggering a frenzy of new construction on an epic scale while simultaneously shrouding the entire scene in a thick, obscuring dust cloud. This is not a metaphor for urban planning, but a precise description of how galaxy mergers work, and it offers a powerful solution to our age paradox. What our telescopes might record as a single, serene, and ancient red galaxy could, in reality, be the recent firestorm aftermath of two gas-rich, star-forming galaxies crashing together. This cosmic collision compresses billions of years of evolutionary history into a brief, spectacular flash. The process begins with two galaxies, each rich with the cold hydrogen gas that fuels star birth, drawn together by their mutual gravity. As they begin their final approach, their delicate structures are torn apart by immense tidal forces. These forces violently compress the vast reservoirs of gas within both galaxies, triggering a tsunami of star formation known as a starburst. In a short period, perhaps only a few tens of millions of years, the merger can produce a staggering number of new stars, outshining the combined light of the two original galaxies. Many of these newborn stars are massive, hot, and blue, but they are born into a scene of cosmic chaos. The same collision that created them also churns up enormous quantities of dust from the interstellar medium. This dust, a product of previous stellar generations, now billows out, enveloping the entire galactic core. Here is where the visual trick occurs. The dust acts as a colossal filter, absorbing and scattering the brilliant blue light from the young, hot stars. What finally escapes the galaxy and travels across the cosmos to our telescopes is the reddened, longer wavelength light that can penetrate the dusty shroud. The galaxy's spectrum, therefore, carries a confusing mixed signal. It has the strong emission lines of intense, ongoing star formation, but its overall color is the deep red we associate with old age. Our models trying to interpret this blended light can be fooled. They might see the red color and infer a dominant population of old, cool stars that have been quietly aging for billions of years. In reality, they are seeing the glow of a stellar nursery masked by its own soot, a galaxy that is not ancient but violently adolescent. Furthermore, the merger itself creates the illusion of greater mass and maturity. Two smaller galaxies combine their stars and gas, instantly creating a single object that appears more massive and structurally settled than either progenitor. The gravitational upheaval can also funnel gas toward the center, feeding the supermassive black hole and igniting a quasar, whose intense radiation further heats the dust, adding to the complex infrared glow. So, a single observation captures a snapshot of this brief, hyperactive phase, a massive, red, seemingly quiescent galaxy. The timeline collapses. We do not need to explain how one galaxy slowly grew old over many billions of years. Instead, we have a scenario where two young, active galaxies, in a relatively short and furious event, created something that perfectly mimics the appearance of great age. The galaxy is not older than the universe. It is a brilliant cosmic masquerade, its true, violent youth hidden behind the curtain of its own creation. The universe's most prolific star factories are often its most deceptive. Among the most extreme examples are the submillimeter galaxies, cosmic behemoths that shine not in visible light, but in the far infrared and submillimeter wavelengths, a realm invisible to our eyes. These are not serene islands of old stars. They are frantic, dust-choked cauldrons of creation operating at a pace that defies belief. A single submillimeter galaxy can form stars at a rate hundreds or even thousands of times faster than our own Milky Way, birthing the equivalent of a new sun like our own every few hours. Yet this furious activity is almost completely hidden. The immense clouds of dust generated by this stellar frenzy absorb nearly all the visible and ultraviolet light, converting it into heat. This thermal energy is then re-radiated as a deep, warm glow at much longer wavelengths. To an observer using only optical telescopes or even near-infrared instruments, such a galaxy might appear as a faint reddish smudge, a signature easily mistaken for the gentle light of an ancient quiescent stellar population. It is the ultimate cosmic impersonation, where a galaxy's brilliant youth is veiled behind the soot of its own astonishing productivity. This is why multi-wavelength astronomy is not just helpful, it is essential for cosmic truth. Relying on a single slice of the electromagnetic spectrum is like trying to understand a roaring city by listening through a single, thick wall. You might hear a muffled, low hum and mistake it for quiet industry, completely missing the symphony of construction, traffic, and life happening just on the other side. To see a submillimeter galaxy for what it truly is, astronomers must combine the view from many different cosmic windows. Optical and near-infrared data might show that faint red smudge. But when complemented by observations from space telescopes like Herschel or ground-based arrays like the Atacama Large Millimeter Array, a dramatically different picture emerges. The submillimeter data reveals an intense, blazing core of thermal emission, a sure sign of vast quantities of warm dust. Further observations might detect the specific radio waves emitted by carbon monoxide gas, tracing the vast reservoirs of cold molecular fuel feeding the starburst. Only by stitching together these disparate views, the optical redness, the infrared heat, the millimeter wave gas, can we correctly diagnose the galaxy's true condition. We see it not as an old relic, but as a colossal, dusty nursery in the midst of a breathtaking growth spurt. Its light tells a story of simultaneous creation and obscuration, a paradox resolved by looking at the universe in all its colorful complexity. For the earliest galaxies observed by James Webb, this multi-wavelength approach is our most powerful tool for demystifying the age puzzle. A galaxy that appears red and mature in Webb's near-infrared images could indeed be a genuinely ancient system. Or it could be a submillimeter galaxy in its infancy, its dazzling blue starlight already transformed to infrared warmth by intervening dust. The key is to seek corroborating evidence across the spectrum. Does the galaxy's emission show signs of strong, ionized gas typically found in stellar nurseries? Are there signatures of complex molecules or dust features that point to a rich, processed interstellar medium? By building this complete spectral portrait, astronomers can begin to weigh the likelihoods. They can estimate the dust content, model its filtering effect, and back-calculate to the intrinsic color and age of the stellar population underneath. In many cases, the solution emerges. The galaxy is not older than the universe. It is simply younger, dustier, and far more violently active than a single snapshot could ever reveal. This process turns an impossible age into a comprehensible, though still extraordinary, phase of galactic evolution. The mystery softens not because the data was wrong, but because our interpretation has grown more sophisticated, learning to see the heat of the forge behind the smoke. The James Webb Space Telescope is not creating a crisis, it is providing the evidence to solve one. Its early observations delivered a stunning collection of puzzling red galaxies, but the telescope's true mission has always been to investigate, not just to inventory. We are now moving from the era of first impressions into a period of deep, forensic analysis. The initial flood of photometric candidates, while breathtaking, was always a starting point. The real work lies in the meticulous follow-up, and that process is already underway with transformative results. For some of the most extreme early candidates, Webb's powerful spectrographs have now delivered definitive verdicts. In several notable cases, the spectroscopic redshift has been significantly lower than the initial photometric estimate. These galaxies are not the impossibly ancient giants from the cosmic dawn they first appeared to be. They are closer and often dustier objects whose light was misinterpreted by our broad color filters. This is the scientific process in action, self-correcting and refining its view with better data. It echoes the lessons learned from the Hubble Deep Field decades ago, reminding us that extraordinary claims require not just extraordinary evidence, but the most precise evidence we can possibly gather. Yet for other candidates, the story is different. Webb's spectra have confirmed their extraordinary distances, placing them firmly in the universe's first few 100 million years. For these confirmed giants, the paradox does not vanish. It simply becomes a sharper, more well-defined problem. The telescope is providing the crucial data we need to test our models against reality, separating cosmic illusion from genuine physical challenge. It is giving us the detailed stellar spectra, the chemical fingerprints, and the dust maps required to move beyond guesswork. We are no longer asking if a galaxy is red. We are now able to ask why it is red, and what specific combination of age, dust, and star formation history produced that exact signature of light. This shift from cataloging to diagnosis is the heart of the ongoing revolution. The path forward is mapped out in a series of ambitious, coordinated observational campaigns. Large international teams are now using Webb for deep spectroscopic surveys, targeting hundreds of high redshift galaxy candidates to build a statistical sample. This will tell us not just about the most extreme outliers, but about the typical galaxy in that era. Other programs are focusing on the detailed internal physics of individual systems, using Webb's unmatched resolution to study how gas and stars are distributed within these infant structures. Simultaneously, observations from other great observatories, like the Atacama Large Millimeter Array on Earth, are crucial. They provide the complementary long-wavelength data needed to measure dust content and cold gas reservoirs directly, completing the multi-wavelength portrait. Each new spectrum is a piece of the puzzle, and the picture that is emerging is not one of a broken universe, but of a cosmos whose first chapters were written in a dialect we are only now learning to read fluently. The paradox is not being erased, it is being precisely measured, and in that measurement lies the key to a deeper truth. The evidence presents us with a cosmic scale, balancing two very different kinds of explanations. On one side, we have the possibility of systematic error. On the other, the thrilling prospect of new physics. The weight of the evidence as it accumulates is beginning to tip decisively. Consider the case for observational mistakes. Photometric redshift errors remain a real concern for many candidates, and the historical precedent from Hubble is a powerful lesson in caution. Dust reddening and modeling degeneracies absolutely can, and do, create the illusion of impossible age. These are the prosaic, often messy, realities of astronomy. They are the first filters any extraordinary claim must pass through. Yet, as the James Webb Space Telescope and other instruments gather more definitive spectroscopic data, a pattern is solidifying. For a growing number of these early, massive galaxies, the high redshifts are being confirmed. Their light is not a trick of cosmic dust alone. The spectroscopic barcodes are real, placing them firmly in the universe's first few 100 million years. This does not eliminate modeling uncertainty, but it dramatically narrows the room for error. We can no longer dismiss the entire phenomenon as a measurement illusion. Something physically remarkable was happening in the cosmos's first chapters. This leads us to the other side of the scale, the need for new astrophysical understanding. The data is compelling us to accept that the early universe was a place of astonishingly efficient and rapid construction. The first galaxies did not assemble with the slow, stately pace we see in the later universe. They were born in a frenzy, a kind of cosmic gold rush where the rules of star formation and black hole growth were written in bold, fast strokes. The most likely solution now emerging is not a complete overthrow of our cosmological model, but a radical revision of its fine print. The lambda cold dark matter framework, the grand blueprint of our cosmos, remains robust on the largest scales. It correctly predicted the cosmic microwave background and the vast web of galaxy clusters. Its foundation is sound. The crisis lies in the details of how normal matter behaved within that framework during the first critical moments. We are learning that gas cooled, collapsed, and ignited into stars with a speed and coordination we did not anticipate. Feedback from the first stars and black holes may have acted not just as a brake, but as a powerful catalyst, triggering waves of star formation in a rapid, punctuated rhythm. The first dark matter halos may have formed earlier and in a more synchronized way than our simulations predicted. This is not a failure of cosmology, but its evolution. The standard model is being stress-tested, and in the process, it is revealing a more dynamic, more explosive story of cosmic dawn. The galaxies are not older than the universe. They are proof that the universe's childhood was far more eventful, far more productive, and far more brilliant than we ever dreamed. This search for our deepest origins is more than an academic exercise. It is a journey to understand the very foundations of our own existence. Every atom of oxygen in our lungs, every particle of iron in our blood, every speck of carbon that forms the backbone of life itself, was forged not in the Big Bang, but in the hearts of stars and the cataclysmic explosions that ended their lives. Those first galaxies were the universe's primordial foundries. Within their turbulent cores, the first generation of massive stars lived brief, brilliant lives, and in their spectacular deaths, they scattered the first heavy elements into the void. This enriched gas became the raw material for the second generation of stars, and eventually for rocky planets and the chemistry of life. We are literally stardust, and the story of how that stardust was created and distributed begins in those enigmatic early assemblies of light. By unraveling how quickly they formed and evolved, we are tracing the supply chain for the building blocks of everything we know, including ourselves. The Milky Way, our own majestic spiral home, was once one of these infant systems. Its ancient halo contains stars that are nearly as old as the universe itself, silent witnesses to that first era of frantic construction. To understand the bizarre galaxies at the cosmic dawn is to read the opening chapters of our own galaxy's biography, a story written in the faint, reddened light of its most distant ancestors. This mystery, therefore, is not a remote curiosity. It is a direct investigation into our cosmic heritage. The pressure to solve it has become a powerful engine for human ingenuity. To peer further back in time, we had to build the James Webb Space Telescope, a marvel of engineering that pushes the boundaries of optics, cryogenics, and infrared detection. Its very existence is a testament to our desire to answer these fundamental questions. The theoretical challenges posed by its data are forcing a renaissance in astrophysical modeling, driving the development of more sophisticated supercomputer simulations that can capture the chaotic interplay of gravity, radiation, and chemistry in the infant cosmos. Each proposed solution, from exotic dark matter to rapid black hole growth, stretches our imagination and refines our grasp of physical law. The age paradox is a catalyst. It exposes the limits of our current knowledge, not as a failure, but as a bright beacon pointing toward the next frontier of discovery. In wrestling with galaxies that seem to defy time, we are ultimately learning how a universe of simple, primordial energy transformed itself, against all probability, into a cosmos rich with complex structures, chemistry, and the potential for life. The answer will not just tell us when the first stars switched on, but how the universe learned to build something as wondrous as us from the ashes of its first brilliant fires. The journey from cosmic paradox to profound understanding reveals the true nature of scientific discovery. We began with a seemingly impossible statement that some galaxies could be older than time itself. This was not an error in the cosmos, but a challenge to our perception, a brilliant spotlight shining on the limits of our knowledge. Through the patient work of observation and interpretation, we have watched that stark contradiction soften into a far more fascinating reality. Galaxies are not older than the universe. Instead, our most powerful telescopes are showing us a universe whose first acts of creation were executed with a speed and efficiency that left our models struggling to keep pace. The infant cosmos was not a slow, stately place. It was a dynamic, explosive workshop where dark matter scaffolds formed with startling haste, where gas collapsed in monolithic bursts, and where the first stars and black holes grew up together in a furious, symbiotic dance. What appeared as a serene, ancient glow was often the masked brilliance of youth, a cosmic adolescence shrouded in the dust of its own incredible productivity. This resolution does not diminish the mystery, it elevates it. We have traded a simple impossibility for a complex and thrilling truth about the universe's formative years. Such is the path of science. It is not a straight line from ignorance to answer, but a winding road where each apparent contradiction becomes a signpost pointing toward a deeper layer of reality. The paradox forced us to check our instruments, question our assumptions, and refine our theories. It pushed engineers to build a telescope like James Webb, and it now drives theorists to rewrite the recipes for the universe's first moments. This is how human understanding grows, not by confirming what we already know, but by being persistently surprised by the cosmos. As the data continues to stream in from observatories around the world and in space, this story is still being written. The final chapters on Cosmic Dawn are yet to be composed, and they will be authored by the next generation of curious minds, looking up at the night sky and daring to ask the next impossible question.